We are going to cover polynomial functions with this lecture video. So just quick summary. So we are going to cover end behavior using the leading coefficient test. We are going to cover solving polynomial functions along with stating the multiplicity of those. We are going to get into the intermediate value theorem, and all of that is going to lead us to where we can graph polynomial functions there. All right, so starting here from the beginning. So looking into polynomial functions. So we should know that a polynomial is just a combination of variables, constants, all jumbled together, right? It could be a single term. It could be a long, 100-term polynomial. So there's a lot that could be going on in these types of problems. So we're going to try and narrow that down. And one of the first things that we're going to talk about in looking into graphing a polynomial function is end behavior. All right, so essentially taking a look at a graph. What is it doing at the end? What is it doing on the left side of the graph? What is it doing on the right side of the graph? So just real quickly here. All right, so the higher in degree that we go with the graph, right? If I have anything x to the first power, that's going to look like a straight line. If I have something that's x squared, right, that's going to have our parabola shape. X cubed is going to look something like this, right? X to the fourth is going to be our w's. X to the fifth are going to kind of just go another step further and look something like this. But the higher in power we go, the more turns in our graph, the more turning points we're going to have here, or in my brain, the more squigglies we kind of have that are going on in the center of our graph here. All right, so we kind of focus first, what's going on in the end? If we take a look here, our x squared and our x to the fourth graphs, if we ignore what's going on in the middle, they have the same behaviors here to the left and to the right. They both go up on the left. They both go up on the right. All right, if I have my x to the first, x cubed here, I drew a negative for the x to the fifth, so I can't use this as an example here. But x to the first, x cubes, these are both positive examples of those. So if you notice for our odd powers, if we cover up the middle of the graph, well, on the left side, they're both going down, and on the right side, they're both going up. They follow the same patterns. They follow the same behavior. Based off, is the degree even or odd, and is it positive or is it negative, right? Positive version of the graph, negative version of the graph is what we're going to be looking at here. So this little chart here is going to help us with that. So essentially, this top row says when a sub n is greater than 0. So a sub n is our leading term of our polynomial. That's what we want to focus in on here, is we want to focus on our leading term, specifically the sign and the degree of that. And based on the sign and the degree of our leading term, we should know what the end behavior is. If our leading term is positive, that's going to be this first row right up here. Even power, odd power. So it's positive and it's even, our end behavior is going to go up in both directions, just like a positive x squared. If it's positive and it's odd, so that's going to be something like this. Think of a positive x to the first here. It's going to go down on the left and up on the right. Well, the bottom row here is just if it's negative. So a negative parabola, so think about that. Negative, even. I always just compare it to a negative parabola. A negative parabola is going to go down, in both directions here. When I think about negative and odd, I always just think of the negative x to the first, right? I know that it's going to go up to the left, and I know it's going to go down to the right here. All right, so rises to the left, rises to the right, falls to the left, rises to the right, falls to the left, falls to the right, rises to the left, falls to the right. So that's kind of the language that most of your math books are going to use with this here. So this is kind of just a quick little chart here to kind of help you answer, to use the leading coefficient test to determine the end behavior of your graph. It's typically the first step in graphing here. So let's see if we can do that real quickly here with these 4 examples. Example A, again, we want to focus on the leading coefficient, so the leading term here. And if we look at that, so we have a positive x cubed. So positive, I want to look at the top row. X cubed is odd, so it's going to have this end behavior right over here. It's going to falls to the left, and it's going to rise to the right. That's all it's looking for here. That's all we're answering. It falls to the left, rises to the right. If we look at our next example, this is negative, and it is an even power, right? Negative sign, even power, right? 2, 4, 6, 8, 10, all the same. We just care is it even or odd. So negative is the bottom row, even is this one here, right? So bottom row, we want that first column. So it's going to fall in both directions here. So it's going to falls to the left and falls to the right. All right, so it's essentially just comparing. Once you have your chart, it's a matter of just looking at your leading coefficient, your leading term, and comparing it here. Moving on to example C. So example C, this is given to us in factored form. So it's in factored form, we do need to know the leading term of this here, or what that would be. So it's going to be just a little bit different when they're in this form here. When they're this form, we're still going to look at the leading term for the sign. This one definitely tells us that this one's negative. This one over here for D, we do know that it's positive, right? Otherwise, think of it this way. Look at your powers for each one of these factors. Here we have x cubed, right? So that has a power of a 3. This factor here is x squared, right? So a power of a 2. This factor here doesn't have a number there. It's understood to be a 1. Add all of these together. 3 plus a 2 plus a 1 is a 6. So this is really a power of a 6, right? If we multiplied x cubed times x squared times x, which is really what this is, it's going to be x squared. And it's going to be negative because of this negative here. So that means it's going to be negative, even power. So negative is less than 0, even power is here. It's going to fall in both directions. So falls to the left and falls to the right. Last example here, we already said that it's positive. So let's see our powers here. We have 3 factors. The first one is cubed. The second one is to the first. The third one is to the first. So 3 plus 1 is a 5. So we have a positive polynomial to the 5th degree. So if it's positive, again, that's our top row. 5th is odd, so let's see, that's going to fall to the left. And it's going to rise to the right. So after we're able to determine the end behavior of our function, the next step in graphing is to solve that polynomial function so that you can get your zeros, so that you can get your x-intercepts there. So let's say, for example, that we knew the end behavior went up in both directions here. The next thing we would want to do is we would want to find our zeros here, and let's just say it was something, I don't know, like this, right? So at this point, you should already know how to solve a polynomial function, but one of the other extra things that we're going to talk about here is stating the multiplicity of a given zero. So a 0 can have an even or an odd multiplicity. So there's 2 ways that you essentially could kind of look at that. Your 0 can have an even multiplicity if it shows up an even amount of times, or if it has an even power for that 0. So for example, let's say you solved an equation and you got like x equals 2, x equals 2, x equals 1. The x equals 1, well, that 1 showed up 1 time in your solutions, whereas the 2's showed up twice, right? So because the 2's showed up twice, you would only mark that 2 once on your graph. But the fact that it showed up twice means it has an even multiplicity because it showed up an even amount of times. What an even multiplicity tells you here is this. If it has an even multiplicity for your graph is going to touch the x-axis and it's going to turn around. So what that means here, so let's just say our graph was going this direction here, right? So if this 0 here has an even multiplicity, when your graph gets to it, it's going to touch it and it's going to bounce back, kind of like a magnet. That's what an even multiplicity tells. For an odd multiplicity, if your solution only popped up 1 time, I know this is x equals 1, but let's just pretend it's on this one here, or this one here. Let's just say, so your graph is approaching that one. An odd multiplicity, it shows up 1 time, 3 times, 5 times, right? In this instance, 1 time. It's going to, an odd multiplicity says the graph is going to cross at that point. So when your graph gets to that point, it's going to cut through completely. So it makes a big difference on your graph, right? Even number of times it's going to touch and it's going to go away. odd number of times it's going to cut through. So it is going to make a difference in graphing so that you know exactly what to do at these points. So for the next 3 examples, let's go ahead and solve these polynomial functions, find the zeros, and then state the multiplicity of those zeros. Example E, I always consider this one our easy example. This one is already factored for us here. So if it's already factored for us here, we can use the zero factor property, split your factors up, set them each equal to 0, and solve. Okay. So when we set these each equal to 0 and solve, so over here, we're just going to subtract the 1/2 on each side, and x is equal to a negative 1/2 as our first solution. Over here, we have x minus 4 cubed is equal to a 0. We could cube root each side. That is going to disappear on each side, right? A cube root in a cube is going to cancel, and a cube root of 0 is just a 0, where we are going to add that 4 on each side. So x is equal to a positive 4 as our second solution here. So stating the multiplicities of these then. So if I take a look at my work, it looks like each one just showed up 1 time here. So in addition to what I just mentioned here, so multiplicity could be how many times did that solution pop up, but also what degree, what power did that 0 hold? If we go back up to our factored form here, this x has a power of a 1, which means its multiplicity is just going to be a 1. This factor over here, x minus 4 to the third, this has a power of a 3. So that means the solution for this one is going to have a multiplicity of a 3. That 4, again, holds a multiplicity of a 3 because it's cubed here. All right, so for x is equal to a negative 1/2, this has a multiplicity of a 1, whereas the 4 has a multiplicity of a 3. Regardless, they both have odd multiplicities, and if we were to graph these, we would completely cut through those points. Moving on to our next example here. So first we need to solve this, and if we're going to solve this, we're going to go straight to factoring here. So I'm going to factor out an x first. And then let's see, let's factor this trinomial here. X times x gives us x squared. It looks like these are going to be 1s with both of those being negative here. So x is going to equal 0, x is going to equal 1, x is going to equal 1, right? So set your 3 factors equal to 0 and solve. All right, just add the 1s on each side there. So we got 2 different solutions. We got a 0 and we got a 1. This 0 popped up 1 time. If we look at this one here, it does have a power of a 1. So that 0 has a multiplicity of a 1. The number 1, though, the solution that we got for that, it popped up 2 times here. And notice here in our factor, x minus 1, that could be written as x minus 1 squared, right, since we had 2 of them. So this is going to have a multiplicity of a 2. Again, because we got 2 of those factors, we got 2 number 1s as our solution. Again, on our graph, it'll only count for a 0 and a 1. But again, odd multiplicity, even multiplicity here for these. I'm sorry, that's a 1 and a 0. All right, 0 has the multiplicity of a 1, so odd. Number 1 has a multiplicity of a 2, so that one's even. Looking at our next example here, so again, we need to solve this so we can state the multiplicity of our zeros here. So let's go ahead and factor this. So we're going to factor this by using factor by grouping. I'm going to factor out an x squared here up front, which is going to leave me with an x plus 7. Factor out a negative 4 from this back grouping here. And when we factor that out, it's also going to leave us with an x plus 7. And since we have an x plus 7 here in common, factor out that x plus 7, leaving us with the x squared minus 4. And if you need a refresher on factor by grouping, go back and watch one of those videos that I have. I have a good handful of those over factor by grouping to look over. Otherwise, these are our 2 factors here. Notice our 2 factors here that we need to split and solve. They each have a power of a 1. So our solutions should all have multiplicities of 1s here. So let's see, x plus 7 is equal to 0. X squared minus 4 is equal to 0. Solve these 2 equations. Subtract the 7 on each side to get x is equal to a negative 7. Add the 4. Take the square root of each side to get rid of that square. And x is equal to a plus or minus 2. 3 different solutions here, each with a multiplicity of 1, right? They each popped up one time. We got 1 negative 7, 1 positive 2, 1 negative 2. So they each have a multiplicity of a 1 here, all 3 of these. The next thing we're going to talk about is the intermediate value theorem here. So the intermediate value theorem is a test, okay? So we're not solving anything here. Essentially, what this is saying here is it gets used a lot for polynomial functions that maybe are not as easily solvable. Maybe they can't be easily factored or something like that. And maybe we just need to know, hey, is there a solution between these 2 points here, right? Do we have a 0 here or, something like that? We just want to know if we have one in the vicinity. Maybe we can't calculate the exact number of it, but it would be helpful to know if we actually had a solution within this interval or not. And that's what the intermediate value theorem is here for. So what it essentially tells us to do here, it says if we plug in these values here, right? If we want to know, is there a solution between 1 and 2 in this polynomial function? What it's essentially telling us to do, it wants us to plug in the 2 endpoints. Plug in a 1, plug in a 2, right? Or in this example, plug in a negative 1, plug in a 0. If there is a change in sign when you do that, then yes, a 0 exists. So it's essentially saying, like, if I plug in 0 and I get something positive, right? And then I plug in 1 and I get something negative. Well, it would make sense then for it to go from positive to negative here. It would have to cross this line, which means there is a solution there. So if there's a change in sign, yes, there is a solution. But if there's not a change in sign, so let's say I plugged in 1, right, and I got a positive solution. I plugged in 2, I got a positive solution, which means if I were to connect these dots, they're staying up here where it's positive, which means they're not crossing my x-axis, which means there is no solution, no x-intercept, no 0 here. So if there's a change in sign, yes, a solution exists between those intervals. No change in sign, no solution exists. So what we're going to do here is we're going to find f of 1 and we're going to find f of 2, and we're going to compare our solutions here. So when we plug in a 1 here, that is 1 cubed minus 1 minus 1, right? Just plug it into your function here. This gives us 1 minus 1 minus 1, which is a negative 1 there. Plug in 2 then, right? The other endpoint, giving us 2 cubed minus 2 minus 1. That is an 8 minus a 2 minus a 1, which is a 5. This one's negative. This one's positive. There is a change in sign. So yes, a solution exists between 1 and 2. Do a similar thing here for f of x. So we're going to plug in a negative 1 and a 0. So when I plug in a negative 1 here, let's see what we get. That's going to give us a 2 here in front, minus a 4 plus a 1. So that looks like that is a negative 1 there. When we plug in 0, f of 0, so let's see, this is going to be a 0. So essentially we have a 0 minus a 0 is equal to a 1. So once again, yes, a 0 does exist between these 2 points here. Our last 2 examples, we are going to graph the following polynomial functions. So first off here, so let me see. For this graph, the first thing we want to do is look at our end behavior, which means we're looking at our leading term. Our leading term is positive, and it has an odd power. If it is positive and has an odd power, again, remember, positive, odd is going to have this end behavior right over here. It is going to fall from the left and rise from the right-hand side. The next thing we want to do is solve this here. So let's see. When we solve this, again, this is factored by grouping. So let's see. When we factor this, we can factor out an x squared here from this front grouping. We can factor out a negative 1 from this back grouping. It's going to leave us with an x plus 2 inside our parentheses. making that factor into x plus 2 with our x squared minus 1. Solve both of these, so notice the powers on these are a 1, so the multiplicity for these solutions should be a 1. But split your factors up, set them each equal to 0 to get your x-intercepts here. So we have x is equal to a negative 2, and then this is going to give us a plus or minus 1 here. Add the 1 to the other side, take the square root of each side, and x is a plus or minus 1. So let's go ahead and plug those in here. So we got 3 zeros so far, a negative 2, a negative 1, and a positive 1. Let's go ahead and also find our y-intercept. So we can find our y-intercept by finding f of 0, right? Plugging in 0 here gives us 0 cubed plus 2, 0 squared minus 0 minus 2. This is a 0, this is a 0, this is a 0. Our y-intercept is at a negative 2, so down here. And that should be good enough in order to graph this. So this is how we graph this. So from the left, we know our end behavior is coming from this direction, and your graph is going to want to go towards its first point, its first solution here. This has an odd multiplicity, and odd multiplicity means that it's going to cut through. Then it's going to want to turn around, and it's going to want to hit its next point, which is right over here. This negative 1 also has an odd multiplicity, so it's going to cut through there. And it's going to want to go towards its y-intercept. Then it is going to want to turn around and go towards its next point right over here. Again, its next point also has an odd multiplicity. It only popped up once, which means it's going to cut through there. And then it's going to end up following our end behavior as we saw here. So that is what our graph for this is going to look like. Next example here. So next example, if we look at our end behavior, this is negative and we have a positive degree. So it is negative, right? So less than 0 here. I said positive degree, even degree here, right? Negative and even, it's going to go down in both directions here. So that is what our end behavior will look like. Otherwise, we want to go straight to solving this so we can see what our zeros are. So let's see. Factor out an x squared, specifically a negative x squared, right? If your leading term is negative, factor that out. We have an x squared here in common. When we factor that out, we are left with an x squared minus a 4. Split your factors up, set them each equal to 0, and solve. But here you can divide by the negative, you can take the square root of 0, but you're still going to get that x is equal to 0. Add your 4, take your square root of each side, and x is going to equal to a plus or minus 2 there. So we got a negative 2, right, as a 0. We got a positive 2, and then also a 0 here. So taking a look at the multiplicities here. So this factor here was x squared. This one does have a multiplicity of a 2. The only reason we lose out on that second 0 here, there's no such thing as a plus or minus 0, right? This was x squared, this is x squared, all right? So you would typically get 2 zeros here, but there's no such thing as a plus or minus 0, so it's just a 0 here. But it does have a power of a 2. Here, this factor here had a power of a 1. We got 1 positive 2, 1 negative 2. So the negative and positive 2 have multiplicities of a 1. The 0 has a multiplicity of a 2. All right, so even multiplicity, odd multiplicity. That means when we connect the dots here on the left-hand side, it is going to cut through, and it's going to turn around and go to its next 0. But this one here has an even multiplicity, so it's going to turn around and bounce back. And then eventually it's going to loop back around to get our next solution here and cut through to end going in that negative direction.